When an object like a ball is thrown against a rigid wall, it bounces back. This reflection of object can be analyzed in terms of momentum and energy conservation. If the collision between the ball and the wall is perfectly elastic, then all the incident energy and the momentum is reflected and the ball bounces back with the same speed. If the collision is inelastic, then the wall or the ball absorbs some of the incident energy and momentum and the ball does not bounce back with the same speed. Waves also carry energy and momentum. Whenever a wave encounters an obstacle, they are reflected by the obstacle. This reflection of wave is responsible for echoes, radar detectors, and for alarming standing waves. Standing waves are formed by the superposition of two traveling waves of the same frequency with the same polarization and the same amplitude, traveling in opposite direction. This shows a wave pulse on a string move from left to right towards the end, which is rigidly clamped. As the wave pulse approaches the fixed end, the internal restoring forces which allow the wave to propagate exert an upward force on the end of the string. But since the end is clamped, it cannot move. According to Newton's third law, the wall must be exerting an equal downward force on the end of the string. This new force creates a wave pulse that propagates from right to left with the same speed and amplitude as the incident wave, but with opposite polarity. That means upside down. At a fixed rigid boundary, the displacement remains zero and the reflected wave changes its polarity, undergoes a 180-degree phase change. Here, the right end of the string is free to move vertically. This string tied to a ring which slides up and down on a vertical pole. The net vertical force at the free end must be zero. This boundary condition is mathematically equivalent to requiring that the slope of the string displacement be zero at the free end. The reflected wave pulse propagates from right to left with the same speed and amplitude as the incident wave and with the same polarity. That's mean right side up. At free boundary like this, the restoring force is zero and the reflected wave has the same polarity, no phase change, as the incident wave. The figure shows a wave pulse traveling along a string towards its end, which is connected to a small light ring that can move along a vertical wire. Which of the following figures best represent the shape of the wave pulse at the instant when the peak of the pulse reaches the ring? You can see here that a pulse has two half portions. When the peak of the pulse reaches the ring, the height of this area doubles up as of the amplitude of the pulse, and the width of this area shrinks to half as of the width of the pulse, because the two halves of the pulse is stacked on each other. Based on the information we have learned, we have a precise answer here, that is the second one.